Good evening to you all, and welcome to the penultimate Durham Castle lecture of this academic year. I'm delighted this evening to welcome Professor Adrian Bejan here, who is going to speak to the title that is up there. Actually, that's the title of your book. We've got a slightly different title, Life and Evolution as Physics, but it clearly relates to the physics of life and evolution. Adrian is the J.A. Jones Distinguished Professor of Mechanical Engineering at Duke University, where he has been a full professor since 1984. Since then, he has published, and you should pause over this because it's a big number, over 600 peer-reviewed articles, let me repeat, over 600 peer-reviewed articles, a full-time occupation, and 28 books. Not a bad contribution to the world of science and understanding. Adrian is ranked, not surprisingly, among the world's top 100 most cited authors worldwide in engineering in all fields and all countries since 2001. And he's received another big figure, must be physics, 18 honorary doctorates from universities in 11 countries. Speaks for itself. Now, Adrian's research, which I've tried to understand, being a humble social scientist in the last week or two, covers a wide range of topics, including thermodynamics, heat transfer, fluid mechanics, convection, and porous media. I recently learned what that is. More recently, he's developed the constructal, is that what you call it, law of organization and evolution in nature, which means, after studying him on YouTube a great deal, at least which I think now means, after watching him on YouTube quite a lot, by the way, I pushed up his viewing figures considerably, because I kept on playing back and playing back and playing back, as I said, as a humble social scientist tries to get to grips with this, which means, I'm making you wait for it, for a finite flow of a system to live, its configuration must change in time such that it provides easier and easier access to its currents. The world appears complicated, he adds, but beneath the complexity are ever-evolving systems that ease the flow of currents. And no doubt this is among your topics this evening. Please, whether it is or not, please join with me in giving him a very warm welcome.
Okay.
Are you going to stand here?
I think I will act over here. We'll find out how this works. First of all, thank you for coming to my lecture. I'm very flattered to be invited to speak at the Durham University, and I have many people to thank. First, Professor Held, and then Professor Burt, and then your colleagues who work very hard on making sure that I feel at home. I'll jump right into my topic. The broad view of it is that I know that the audience, meaning all of you, including myself, are from areas that are not necessarily associated with life and evolution education. I come from engineering. I come from thermodynamics, which is the science of power, really power, and machines. And for that reason, my chief objective is to persuade you that you already know the topic, that you have your own ideas, and then I hope you'll feel inspired to contribute to this discussion, especially after I finish my prepared slides. I confess that the topic, as I'm now discovering, especially as I talk about my new book, is at once easy, and then because it's familiar to everybody, but at the same time difficult. And the difficulty has to do with the fact that each of us, we feel that we already know what, in other words, we have an opinion about the meaning of these words and how they go together. So my other objective then is to try to explain why I think that the topic is really not only simple but unifying. What happens next? Oh. So to start, you mentioned configuration in the introduction. To start, the world is actually interesting and important to us because it is discernible. Here are two images of everything. Everything in science is called either nature if you come from Latin or physics if you come from Greek. It's everything that happens by itself. It has configuration, it has anatomy on the right and geography on the left. In other words, the animate and the inanimate are together. They are not separated by, say, names of departments on a campus. And so what we have on the screen is a strident, just two examples that speak loudly of the existence of a phenomenon. A phenomenon, the definition of it is an observation that repeats itself billions and billions of times. In physics, because we don't have immensely huge brains to remember all these observations, those observations, meaning the phenomenon, is summarized as a law. And this is why physics is extremely powerful. It is universally obeyed, but it is also a very thin book. The laws are very few. And I will walk you through how few they are very soon. So that's the introduction to the introduction, which is summarized here. My lecture has two parts. The first began already. It is to explain the meaning of the words, right? So in other words, comma, the words I speak, so that you know what I mean by them. And then I will tell you a personal story, actually, of how this new book came out. I was trying to convince first the literary agent and then the publisher to acquire the book. And while understanding the first part, the response from these business people was, yeah, but what does it mean to us? Okay. So I said, oh, okay, then I will explain that in the book and now in this lecture. And I will talk to you about what everybody knows, which is power, technology, lifetime, meaning life and death, also something about business, and then the natural phenomenon of hierarchy and why it is unavoidable, and the unstoppable spreading of knowledge, why that too is natural. So I begin with continuing the first part. For things to change, in other words, to have evolution, this live flow system, we call it in physics, must be free to change. On the screen we have a laboratory experiment of an artificially created river basin, in other words, a flat area with perfectly horizontal sand surface, artificial rain uniformly falling from above. The student makes photographs of what happens on the floor in time. What happens on the floor is always a tree-shaped flow architecture. It is flowing, but it is morphing. It is morphing from left to right. Now we know, in order to flow better, because after all, imagine the first panel where there was no tree. That one was with seepage. That was a swamp, a relatively dead flow system. It was flowing, it was seeping, but it was not as fast emptying as the one on the right. So this is evolution in a nutshell. It has freedom, and it never ends. So what we retain from this first introduction is the fact that that there is a direction in which this movie tape is running. That is the phenomenon, the oneness, the binary choice between rolling to the right or to the left. That is the phenomenon. The world is full of these examples. In fact, the best come from the inanimate realm in which we live and move. Here is a plume of smoke from a distance. This is a curtain of smoke from a brush fire on the right in Chile. But from a distance, all plumes look the same. But this curtain in the beginning was a flat buoyant jet as if coming out of a slit. In time, meaning higher and higher, the stream develops a round cross-section. It looks more like a worm running through its hole in the ground. And that is the direction of morphing. No round plume evolves into becoming a flat plume. Never, you see. This is the one direction of the tape in which the configuration is morphing. So this is how, okay, I'm learning as I'm thinking about these things, meaning I personally am learning that evolution, unlike all of us who have gone to school, was not taught to us by Darwin, the word. Evolution comes from Latin, from a verb, evolvere, which means to roll out, to roll forth. Get it? As if during birth. This is why in the same language, the world or physics is called natura, she who gives birth to everything. So this is a big deal, evolution, and it belongs in physics. And physics is everything. Life, I still don't know how or what I drank that day and 20 years ago, was defined in physics this way. I said, for a flow system to persist in time, and that is the definition of life, which I wrote to live. To stick around, to be worth talking about, is to be alive, okay? It must evolve freely such that it provides greater access to its current. So you have here a first principle in physics, one that's first because there's no deducible for existing laws of physics. And it is really the statement that accounts for all evolutionary design tendencies or phenomena. Why the book is so thin? This big part of physics called thermodynamics was resting on two first principles, the first law and the second law. The first law is, in fact, much older than physics. Physics comes from the discipline from the 1800s. Before that was part of natural sciences. The first law is a law of mechanics, the conservation of energy, vis viva, vis mortua, meaning what goes up must come down, it could go back up again. That's energy conservation, very old. The second law is what the visionaries of, this is now engineering coming with the science of engines, beginning with Sadi Carnot. And then most notably, I must say, William Rankine, just north of here. The second law is the tendency of anything by itself to flow from high to low. Never the other way around. Remember, water under the bridge or over the dam, that's the second law. Now we have the constructor law, which accounts for the direction or the tendency of flow configuration to change over time. One way, not the other way. I like to make drawings, so I put this previous slide graphically in this form. Time, meaning our experience with learning things from books, runs from left to right. The major revolution in physics was the merger of mechanics with caloric things, calorimetry, thermometry, and the conservation of caloric into thermodynamics. I mentioned Rankine. He was one of the three who got the idea, the light bulb coming on in the middle of the 1800s. And I first made this drawing in 1982 when I argued that the lost child of caloric called heat transfer actually belonged in thermodynamics. And then came this next merger, which is that of evolution, a phenomenon of physics belonging in thermodynamics. Because after all, I don't know how many of you have studied engineering. The thermodynamics in engineering is a very, very serious subject, which has two very, very tiny front chapters, of course, the first law and the second law. But most of the book is about making better and better designs. You see designs of power plants, refrigeration plants, all sorts of other things. Well, meaning the book is about this, except that this had no reason to exist in the book because there was no principle. You see, that's the frustration that thermodynamicists have been feeling for 150 years, that of accounting for their own behavior, meaning for the legality of that behavior as scientists. Now they can feel a lot safer and laugh with me at the past and also be more hopeful of the future. Shortly after that, 1996, I began to see animal movement on the planet in similar ways, like a competing movie, if you want, as the movement of water through the river basin. Because after all, the animals, the migration and all this other, flying carpets of migratory birds, these are basically wheelbarrows of water, self-propelled, moving water from here to here, not only from, say, Europe to Africa and back, but from life to death, okay? There's movement of stuff from here to here. That's the legacy of all these life flow systems, bio or non-bio. So with that constructed law, I was able to predict, this is the first thing that came, the straight line, that these things that move should move for greater access, such that, which really means all sorts of things, including not spending too much time looking for food in order to feed the engine that then drives the wings and all the other organs that propel the body in a particular way, this way, which means a speed that is in a particular relationship with the body mass raised to the power 1/6. Of course, with this is called theory now, a purely mental viewing of how things should be. I come from, not from zoology. After I have this formula, then I live this fantastic short period of going through zoology books and discovering that the world actually knew, you see, the constructive law, has known it for a long time and has been obeying it. The insects, the birds, and also this new species called the airplanes, which is actually the human and machine species. You see that? So that's one thing. First comes the idea, then the audacity to bring together things that usually do not belong together. And then this big picture that emerges teaches evolution itself, which is that in the beginning, there were the many and the few. Over time, the cloud grows to the right with fewer and greater. But in this direction, the cloud does not lose its original tail. So the world becomes, we agree with that, more complex, more hierarchical. But what works is kept. That is another way to speak of evolution, but this time in a predictive fashion. Science, those of us who live happy lives in it, is like being in a bar, okay, and you watch maybe a nice football game, and then you like the first drink, this one, and then you get the idea that maybe you'll have a second one, and maybe a third one. Here, that was one, the first for flyers. These were the next two. And on the right, some formulas for those who like math. On the right are the equivalent formulas of what I'm speaking about here. What I showed you on the previous graph was this formula, which is that the speed in the meters per second is roughly 10 times the body mass in kilograms raised to that power. It turns out that the same analysis teaches that for swimmers, the speed, the constructal speed, and of course that turns out to be the speed in the zoology book, is 1 order of magnitude smaller than for flyers. So, and then you can also predict the work that's the work that's spent by the animal to travel a particular distance horizontally on a map. That goes the other way, meaning that the work required by the flyer is 1/10 of that required by the swimmer. Bingo! Now we know why life, really meaningful mass movement of animal water on Earth began here. And then it spread upward on land and above land toward greater access. No reptile that came out of the ocean went back in the ocean. You see, one way. And now, of course, your mind takes you to flying into outer space. That's, of course, even more in the direction of the effortless, you see, for the, right? Get it? Okay. So now we see the big picture in a predictive sense. So maybe a fourth drink at the bar is in order. For those who like words, what I showed you is summarized this way, meaning we know how things should be. Larger animals should travel faster. They should, also predictable, wave their bodies less frequently. They look lazy or sluggish, the whale, the elephant. But in fact, these are the freight trains of animal mass. They are constantly moving, and they are moving fast. They're stronger, meaning weightlifters. That's why there are weight classes in weight categories in wrestling, weightlifting, and boxing. See, because the bigger are stronger. So the founders of modern athletics knew the constructive law. Get it? They knew it unwittingly. Move more mass to greater distance, live longer, as I'll show you very soon, travel farther during lifetime, just like the athletes. Okay, we're still in the same bar. Even a greater fun followed with this. I had a student who, I was teaching, in fact, animal locomotion from the constructive law, and a student of mine who was a swimmer on the Duke team said, listen, I bet you, he said, we should be looking at the evolution of the sport itself. Well, everybody knows that sports records are meant to be broken. So in time, the speed, the winning speed increases, right? And then I said, well, okay, in that case, you should plot not the time here, but the size of the winning athlete. And these are data from the 100 history of recorded modern athletics. He averaged the data, and the line that is shown here in the dark is exactly the same as for the terrestrial animals that was on the 2 slides ago. So, yes, athletics is a small laboratory in which to watch evolution in our lifetime. Biological evolution, and you can tell this in other ways, such as, winning athletes are basically evolving animals, and evolving animals are athletes. How is that? Same with swimming. In fact, the only difference between this slide and the other one is the photograph. Okay, same success, same surprise, including the new question, which is why in the previous photograph, all the finalists are of West African origin, and here all the finalists are of European origin. That too is predictable from the constructive law. Yes, it's in the book, okay? So now more recently, in fact, very, very recently, with the same idea, I will not, this is the reference, one can show, again, in a predictive fashion, that the lifetime of movement, again, obviously horizontally, but moving horizontally on Earth means moving against a resistance that is due proportionally to gravity. The weight of the body is vertical, but the horizontal force that the mover must overcome is proportional to the weight for everything, not just the terrestrial movement, in the water and in the air. Anyway, so it's just one kind of movement, regardless of the medium. And with that, I was able to show that the lifetime should be a particular multiple of the body mass raised to the power 1/4. The life travel, which is the total length of the wiggle described by any of us, or the cat or the mouse, on the planet during a lifetime, should be almost the square root of the size of the animal, such that lifetime divided by the square root is in fact a constant that has universal implications. And just last year, less than a year ago, again, while teaching the subject, it occurred to me that if the animals and the rivers and the winds and the oceanic currents have it, maybe even simpler things have it, such as the rolling stones and turbulent eddies. A turbulent eddy eventually dies. An eddy is a rolling ball of fluid that has an identity downstream to a particular distance, known as the mixing length in the fluid mechanics, and it takes a particular time to that particular depth. Those two things can be now predicted, and it's the same with a rolling stone. A rolling stone doesn't roll forever, or a rolling soccer ball, okay? There's a distance to it and a lifetime. Those are predictable, and they too exhibit the same proportionality between lifetime and the square root of the travel. This, by the way, is an icon of animal movement, meaning here is you can think of it as a rolling stone or as a rolling stone with a motor inside. This is the dung beetle, okay? This is a very old idea, sort of image of life and the continuity of it in Egyptian thinking. And then the surprises continue. We were talking about bones, by the way, just a second ago. Bones, we know, just like the trunks of trees, when the weight is to be supported is greater, then the column has to be more robust looking, which meaning not slender. That is well known. With the constructor law, we explain in this case something else, which is that small, in this case, mammals tend to be most body and tiny legs. In the other direction, you see the horseshoe design of the animal. The legs occupy a bigger proportion of the size of the animal. Next time you run after a mouse on the kitchen floor, you'll be wondering why it looks like a golf ball painted gray and it has almost no legs, you see. I should have drawn here a mouse. This is predictable, you see. Animals the same size, now we're joking, see the same size. And here the animal has lost its body, has legs, not belly. That comes from theory. And now I've walked you to the newest species of movers on Earth. As I said, I call it the human and machine species. The reality is this, that humans are not the naked bodies you see in the anatomy book. Those are relevant when you're on the operating table or on the cold slab at the morgue. That's a good drawing of who we are or were. But except for those special circumstances, we're actually moving, and we're moving encapsulated in artifacts, in this case the airplane. And this is now in a painting that I made with the help of an undergraduate. The complete evolution of the airplane human and machine species from during the past, meaning during its history. And you see here that, well, it's pretty obvious that today things are complicated. There's diversity. However, along with the birth of bigger and bigger such species or specimens, the small ones are still being made. So the small, which are many, continue to emerge as new, hand in hand, if you want, with the few that are large. Even better, or even more, the larger of, say, 1 decade ago are joined by even larger specimens. And the reason for that is called economies of scale, in this universal tendency toward configurations that offer greater and greater access, which means in this domain less fuel spent per seat and for 100 kilometers. That's the jargon in aviation. The larger has the advantage. The larger truck, the larger pipeline, just like the Mississippi big river compared with its tributaries. And so this is all predictable, and that includes predicting the organs that function inside the animal. But the power comes from the following argument. Imagine that for a particular vehicle, which is shown as an airplane, it could be a bird, the organ that is necessary is a pump. I drew it as a heart, you see. Could be the heart of the bird. And the question is, what size should this organ have? There are an infinite number of answers. You see, from 0 all the way to the right. To have an infinite number of answers means to have nothing. Okay? How's that? Infinite equals nothing. The question is, which answer should it be that I choose for making the correct drawing? And the answer comes from this. From thermodynamics, we know that the component destroys power because it resists the flow of currents through it. Imagine blood going through the arteries and chambers of the heart. The larger those openings, the smaller the resistance, right? So larger pump is better. That accounts for the descending asymptote. At the same time, reality is that the pump is to enable the vehicle to move. And that means that the vehicle has to carry this suitcase called the pump. So in the direction toward the larger, the vehicle is penalized. There's a competition or intersection of asymptotes or a trade-off, which identifies the sag and the curve that's the sum of the two penalties. And from there, the discovery that the organ must have a finite size. Again, predictable size. A finite size means that the organ, this one, is really poor compared with the organ that would have been better by itself. But the poor organ is actually the best for the vehicle. And so the vehicle, the animal, or anything else that's big and complex, an installation, is in fact an evolving and getting better construct of imperfect components. This is good news for those in medicine and in biomedical engineering. There's an entire industry of perfecting the organ with all sorts of new technologies. And that evolution of technology never ends. So with that argument, then became easy to predict, again, the history in this case, and the origin of the one-to-one relationship between, in this case, engine size and airplane size. Amazingly tight correlation. The formula is not shown, but is predicted. So engine size, fuel load is also predictably proportional to body size. The range of the vehicle for one load is also proportional to body size. And the most, all of this just like in the birds, the best to me is the image, the geometric, the surprise, which is that the way that the airplane looks when seen from above or from underneath is that the wingspan is essentially the same order of magnitude as the fuselage length. In other words, the big birds have big wingspans, regardless of size. And that kind of surprise is good for the heart of the scientist. Now I'll not discuss these next few slides. Predictable is also a natural phenomenon in technology called miniaturization. There is a tendency toward that. And the reason for that, by the way, is that in time, in order to lower the bottom of this bucket, you must lower both of these asymptotes. So miniaturization is making the component better. Designing the better and better shape for the airplane is decreasing the slope of this line that signifies penalty with regard to the whole vehicle. So that is one tendency in the cooling of electronics. Another one is the natural phenomenon of modularity or vascularization. Everything that's alive, say a muscle or a piping system in a steam turbine power plant, is like this, like that. A stream comes in, and the stream must bathe a volume, which is shown in yellow here, and then that stream must be reconstituted as one stream and taken out. So to the let's say the observer who would like to steal the secret of the design, if you put this vasculature inside a opaque enclosure, the potential thief would not know really what's inside the box. There's only one stream coming in, and the same stream leaving, like arterial blood, venous blood. But in the volume, there is an architecture, which is called vascular, that bathes the volume. It is an architecture that's actually two trees matched canopy to canopy. Here's the one in red, matched, or two combs, if you want, matched teeth to teeth, or interdigitated, if you want. You may think, now imagine a larger and larger flow system, meaning larger and larger muscle, if you want. You may think that to vascularize that would mean to blow up this drawing. Turns out that that is not a good idea, because at larger scales, this one allows easier and easier flow, meaning lower and lower pumping power. In other words, the smartness of this drawing is valid for particularly small scales. At a particular neck size, this one is better. To use this one forever is not a good idea. At even larger sizes, making more complex trees with the latest one as an element is an even better idea. So this is the origin of the meaning of the emergence of vascular design in nature. Again, it is a manifestation of the constructive law. The last portion of my lecture is about still about the human and machine species, now with a kind of a brief review of thermodynamics. basically all the morphing flow architectures, such as the airplane, fit in this blue world. In time they change. They've changed, of course, from domesticated animals to sail ships to all the way to automobile and airplanes. Each such system takes in, people call it energy, but actually it's useful energy. That's the name for it in thermodynamics. Comes as food and fuel. Two things happen. Work delivered to the maker of the contrivance. In other words, the human attaches to himself or herself what's in this blue domain, buys it, pays for it. And then there is necessarily rejection of heat to the ambient. So that's thermodynamics before the constructor law. The constructor law is about what happens to the work and why, and in what direction in time. So the question is listed at the top, what happened to the produced power? Here is the blue disk again with basically heat in, heat rejected, work produced. The work is destroyed instantly. It is destroyed instantly for the purpose of moving something horizontally on the surface of the Earth. That movement destroys, on a one-to-one basis, the work. So from Mars, if there were somebody like me there practicing thermodynamics, the world is really heat in and the same heat out. But because of the contrivance, because of the evolving flow configuration, which is both here and here, something is moving horizontally on a surface perpendicular to which gravity acts. That is the complete picture. And the evolutionary tendency of these flow configurations here coupled with here is toward greater access over time, which means that per unit of fuel used, the movement on the landscape is greater. The better designed or evolved river basin moves its debris farther. That's evolution. I'll go very quickly through this. This movement of our species is visible famously both in time and in space. In time is known as the S-curve phenomenon, the spreading of a living species. In this case is Brewer's yeast. The spreading of a population adopting the use of radios, the use of TVs over time. And here, the use of one of my scientific publications. Yes.
This doesn't flatten off.
Not yet. But having explained why it must be an S-curve, I'm convinced that that S will also reach its relatively flat end. The prediction is really child's play. Again, a homework in an undergraduate course. What spreads originally as an invasion channel, like invading Iraq. We're talking about this at dinner. In other words, the affected area grows as a finger in the immediate vicinity, or say the spreading of iPhones in the immediate vicinity of the stores connected to the supplier. That invasion, because it's a line invasion, reaches the wall. And then the spreading continues by diffusion transversally. The first mode is this. The second mode is that. The spreading is a power law, meaning territory or population growing as time raised to an exponent greater than 1. This is the convex curve, arc. And then continued by a concave portion. Power law, meaning size proportional to time raised to an exponent. There is no such thing as exponential growth. You know the exponential is a function in mathematics. It's a function that rises above 0 at time equals minus infinity. There is no such time here. Everything that spreads starts at time t equals 0, like the spreading delta under the horse. If you can look there, that's a delta right there. It takes about 5 minutes to see growing. Time t equals 0. So exponential is a very, very famous word that's misused in the discussion of growth or evolution. So that's why I teach students to question the words that people speak. Okay, well, where's the constructor law on this? First of all, S-curve is everywhere, not only in the spreading of things, but also in the collecting flows from volume to point or from area to point. Here's the collecting of oil from underground in the empty quarter in Saudi Arabia. Over time, the design has evolved to have a steeper S-curve. Steeper, you see, that's the constructor law. In time, it has evolved from the single well to the dendritic one, which they call the fishbone design in the oil industry. So that's technology evolution is another manifestation of the principle. Oh, by the way, if you're wondering, because there are also people who worry about this so-called exponential growth continuing forever, here is the S-curve of power production, which means dissipation combined in the U.S. and Britain over 100 years. It's already an S-curve. All right. Here is the S-curve of miles driven per year in the U.S. It has already reached the top. That means one technology, which is automobile transport. All right. And here is the curve that's the latest prediction of world population, which is an S-curve. And we flow in space also with evolving configuration. For this, to teach it, I use the Atlanta airport as an icon. The Atlanta airport is really the design to which all modern airport designs are evolving today. It is a design where there's an area with two ways to move on it, because access means to go from any point to the entire area, which means to any other gate. And at the end of the argument, one discovers that the area must have a particular shape, which is the one I drew, which is also the one that the designers of the airport agreed on unwittingly. It is such that the time to walk on half a concourse is the same as the time to ride on the train. That's 5 minutes in Atlanta. It's much longer, but it's the same time on larger territories. And I call it long and fast. It takes as long as the short and slow. In other words, this is the physics of the wisdom behind the statement that it's stupid to hurry up in order to wait. Right? You heard that. By the way, the Atlanta airport is the icon of the urban design. Again, a natural occurrence. In case you are confused by the fact that cities are basically grids, either regular, like in Manhattan, or crooked, like in some old, let's say, European cities. Well, that's not the point. The point is that what flows is the population on the area. If this is the church attracting the parishioners, say Sunday morning, the flow of the people is a tree from area to point, or people returning from a football stadium after the game in all directions, another tree. And the grid is simply the rigid infrastructure that facilitates the coexistence of all imaginable tree-shaped flows on an area. If you want to see them live, do what I did, which is photograph the making of Belgian waffles. That's the batter, okay? This is earlier, this is later, tree-shaped flow. Or if you, your mind is even faster, you can watch the growth of a snowflake, okay? A tree-shaped flow. a live flow system because it has flow and freedom to evolve. The summarizing feature of all these designs is the few large and many small. That's also known as hierarchy, which is natural. In addition to the examples I showed, here is the arrangement of a freight in a country or in a city or in a county. Few large trucks vehicling the same freight as many small vehicles that cover transversal areas, or the food chain on a particular territory. Few large and many small collaborate in order to mix, along with the vegetation that feeds the small, collaborate in order to mix the soil much better than in the absence of biological flow systems. There are many more examples, much older. The river and the hill slope. River and hill slope. Inhaling and exhaling. Air tubes is the long and fast diffusion transversely into the wall of the alveoli is the short and slow. The slaughterhouse floor is the few and large going long, and the parts being traveling to the sides. The auto assembly line is the inverse of that. The glove inside out. The parts coming together into one large body that leaves as a car. In fact, for those who love history, the slaughterhouse is what gave Henry Ford the idea of inventing the auto assembly line. So you see, this is now the Atlanta design on a much greater scale. The long and fast are the air routes in red. The yellow is the territory that's covered more slowly, but it's shorter, covered by vehicles such as by buses, cars, and other forms of land transportation. The long, remember, the time is the equality of times is the secret. The long route, say from Paris to Moscow, which is long, goes hand in hand with thicker yellow interstices. Get it? So this equilibrium of times is the secret. And now the larger is the scale with which we're familiar, the world itself, the globe. This is a true picture of air mass movement on the globe. These images indicate cumulative condensation trails behind all the aircraft flowing on the globe. So you see what, the whole globe is flying, but it is in fact a vasculature with a heart, and the heart has two chambers. Basically, the Roman Empire, and then what happened after it arced over in this direction. You see, that's the world. And at the bottom, the thermodynamics review. Fuel is used with purpose for the purpose of producing work. Purpose meaning in the contrivance that this human and machine species has conceived. And that work is then converted through dissipation into mass moved to a distance. The picture shows that the movement is hierarchical. Most of it is in the red. No pun intended. It's actually thriving. So that means that the fuel use is hierarchical, naturally. So when next time you hear that the future belongs to those in the advanced countries cutting down on fuel consumption so that the others would get to burn more, then think about this natural architecture that was not designed by one person. It came out of the wishes of easier movement of everybody on the planet. It's not just transportation, but everything on Earth is in fact distributed hierarchically. The the fuel used for heating, for cooling, for producing fresh water in arid regions. All of it leads to this design or feature called hierarchy, where few large and many small. Here's the fuel use per year. This is from data from United Nations. On the ordinate is the so-called wealth index, the gross domestic product. Shockingly, a one-to-one relationship, meaning a line. You see, recognize the territories. Some would say that this should be so simply because up there are the big and here are the small. Well, on a per capita basis, one gets essentially the same alignment with a relatively thicker cloud. So that's a fuel use per capita per year. This is wealth, obviously, per year. And the same alignment, now you know. In fact, you don't know why, but you recognize in the upper, meaning at the head of this organization, the advanced countries. But you also recognize something very, I would say, educational. It is that per capita, the inhabitants of the advanced countries, such as the UK, the US, Japan, per capita, they are burning as much fuel as the inhabitants of Russia. But the advanced citizen is 10 times wealthier. And that discrepancy is no discrepancy at all. It is that the advanced are actually living in the heart of the world, and that means that through them flows everything that sustains the lives of everybody else on the planet. So the big movers are moving not only themselves, but they're actually enabling the movement of everybody else. That's the big picture of who we are. The tendency, of course, is for everyone to race upward. This is, in fact, well documented. Of course, everybody wants more wealth, every country, every individual. That's why the use of fuel is unstoppable. But the direction toward more movement is summarized by me graphically in this slide. I should have painted this territory, which is an invasion, in red, and the rest in blue. The red possess movement, of course, because they possess knowledge. Knowledge is defined as not only idea, but the implementing of the idea, the design change. So those who are leading the design are here. Those who don't have it would like to have it. So the advancement is spreading naturally on the globe. And that spreading is contagious. It's unstoppable. I end with another graphic aid that I made. Now, going back to the simplest summary possible, in thermodynamics, a box like this is known as a system. System is what you, the thinker, choose for contemplation or for discussion. The rest of the world is the other system, is known as the environment. So when I hear people talking about that nature is complicated, I laugh, because in thermodynamics, nature is really simple. It just consists of two things: my system and everything else. It's like a team with just two players, you know. Oh, it's like a boxing match. How's that? A boxing match. Two things interacting. And in this box, or through this box, the environment is blowing a wind. And for the sake of argument, we assume the wind is steady. It's not changing at all. But look what happened in the box in time. This is an Egyptian galley, a galley. And this is the time of Columbus. And this is around 1800, right before steamships. So the architecture, this is evolution. The architecture changed in order for, through configuration, through contrivance, in order for the wind to be responsible for moving mass to greater and greater distances. The same wind. If you don't like that idea, well, you can look at the automobile. Assume that it's, here I made the automobile to be the same size, you see. In the beginning they were smaller, but anyway, same size. All of the same brand, all of them Peugeot. All right, so same fuel stream in, never mind the exhaust and stuff, but in time, greater movement, thank you, greater movement to the right. That's evolution, and the good news is that this film and this one, they do not end. So that's the end of my talk. I told you two things, really. The meaning of the words from physics. And then I talked about us as an introduction to an even longer discussion in that sports bar about us right here. Okay, thank you very much.